Good morning.
Morning. So I'm a little bit behind. I'm going to have to catch up. Uh, Not today, but next week. We're going to have to do an additional session, not additional session, but additional chapter, because we're one chapter behind, and we cannot fall behind. Courses are jam-packed with information that needs to be covered because of the fact this is a core course, and so I can't just like slow up and decide, I'm going to skip this or skip that. It's not, I can't do that because it is a core course and it has a final exam that's supposed to cover certain topics. So I will have to make it a little faster next week. And just I wanted to let you know. And you do have these recordings. You can always go back and listen to them again. Um, because we have to be on schedule for each of the tests and the final exam, everything else like that. All right, so I wanted to do a little review of chapter 8 in terms of problems at the end of the chapter. Then we're going to cover chapter 9 and also do a couple problems at the end of chapter 9 also, which I will post. Both chapter 8 and chapter 9 problems, like I did for chapter 7. I'll post those also on Canvas. All right, so I'm going to share the screen and let's get to chapter 8.
I'm sorry, did you say we're doing something else after chapter 9 today?
No, I didn't say anything like that.
Oh, okay.
No. All right, so let's see, chapter 8. What happened here? All right, just hold on 1 second here. Let me just open up this one. This is actually says chapter 9, but I'm going to click chapter 8. All right. So chapter 8, 8.10 at the end of the chapter is the one that I'm going to focus on. And also, let's see what other 8.15, 8.19, 8.23, 8.30. All right. There's a few of them. And again, please, if this is going too fast, apologize, but I do have to cover material. So if you do, you will have the recording. Remember, the recording is there. These PDFs will be posted. You can follow along at your own pace when you get when you do this on your own. All right. You don't have to know this perfectly during class. I'm just going over the things that you need to know. That's all. All right, so 8.10 is the first one. So let's go to the, share this and go to the actual, I sound choppy, yeah. Sorry about that. Sometimes that happens with Zoom. The best that I can. All right, so let's share the screen, go to the ebook, go to number 10. All right. Draw a picture of bell-shaped curve with a mean of 100 and a standard deviation of 10. This is what I'm looking for. Hold on 1 second. I'm a little clear about something here. Let's go back to the.
Excuse me, Professor, real quick. What time do we start the quiz?
There's no quiz today because I haven't covered everything. So that's the other thing. 2 quizzes next week, one on Tuesday, one on Thursday. I'll tell you more about that at the end of the session. All right. No quiz today. All right. So 8.10. Oh, all right. Page 450. Let me just set something out here for a second. I think I am looking at the wrong textbook. So I apologize for that. This cannot be the right textbook. All right. Give me a second here. from another course. All right, let's actually go to the apologize for that. That was from another course. So it's not even the right textbook. All right. This is referring to a page number that's doesn't exist in your book. All right, let's go back to the ebook. All right, what I want to go over is number one. I'm going to go over these just as we look at the problems. So number one says, using the table. The table is this thing here. This table here is using this table. Or a calculator, determine the percentage of the population falling below each of the following standard scores. Now remember, a standard score tells you how many standard deviations you are above or below the mean. So -1 means you are 1 standard deviation below the mean, all right? So you want to know what percentage of the population has scores below 1 standard deviation below the mean. So we'll go to the table, and the way to figure it out, so you look for -1, which is right here. All right, so it says standard here. I'll go to the top here. It says standard score. So you just scroll down till you find -1 right here. And then here is the proportion below, which if you multiply by 100, which is this number here, 16. So 16% of the population scored below a standard score of -1. All right, so that's what they mean by this. Just look for the standard score and then go across and look for the proportion or percentile. Proportion or percentile just means 100 times the proportion. Now, 1.96 is a famous one. You don't know that, but it is. So we look for our standard score of positive 1.96. The positives, by the way, are in this column over here. So standard scores of 1.96 is right here. And notice it has 0.97 or 97%. For portion below that score. And then 0.84 is right here, and it's 80% below. Right? So that's how you read the table. You just look up the standard score and just go to the next column. It gives you the proportion or percentage. All right, so I just wanted to show you that problem so that you know how to read that table. You do have the table with, in the book. It's in your book. It's in the ebook. It's in the book. So you can actually refer to it. Using table 8.1, determine the standard score that has the following percentage. Now here you're working backwards. You have to find the percentage and then look for that standard score using that table. For example, the percentage of the population below that value, which is 25% below, all right? We're looking for the value, the standard score, where 25% of the population is below that. Now, the 25%, anybody remember what 25% below is? That special name we call it?
The percentile?
Well, it is a 25 percentile, but there's a special name for it. It's called the lower quartile. The lower quartile. And B, 75%, that's the upper quartile. Remember that when we talked about box plots, all right? So these are the special percentiles, 25%, 75%. Now we want to find the standard score corresponding to these two. So how do we do that? Again, with the table. And this time, we're going to look at the percentile column, and we're going to look these up, and then go to the left and find the standard score. All right, so it's just we're working backwards here. So for the 25% one, here's 25 percentile right here, and we just go to the left and we see -0.67. And then we look for the 75th percentile. Well, that's here, over here. We go to the left, it's 0.67. The 45th percentile, Okay, well, we have to look for that. Where would that be? Well, it looks like we have to scroll down on the left here. Here's 45 right here, 45 percentile. Go to the left, negative 0.13. And then the 98th percentile is right over here, 0.98, 98th percentile, and we go to the left, it's 2.05. All right, so we can, if we're given the percentiles, we can find the standard scores from them. All right, so I just wanted to, again, show you these things so that you know how to read the table, look things up. Another one where you can look up things. Here's another one where it says, determine the standard score that has the following percentage of population above it. Above it. So you have to think a little bit here, right? So we're looking for the standard score where 2% is above it. Can you tell me what the percentile is for 2% above? It requires a little bit of mental math here. If 2% is above a certain number, what's below it? What percentage is below it?
98.
Very good, 98. 100 minus 2%, right? That's very good, 98%. And we already found that in the previous problem, the 98th percentile. So 2% above is the 98th percentile. How about 50% above? What is that called, by the way? Special name for that one, 50% above.
The higher quartile.
No, higher quartile is 75% below or 25% above. What's 50%? 50%.
Oh, low.
50% above also means 50% below. You're splitting the data set into two equal pieces. What is that called? Anybody?
Mean.
Not the mean, you're close.
I just looked at this last night.
Anybody? The name is very
Is a name for it. Is it the standard deviation?
No, it's the median. The median.
That's what I said in the beginning. I said the median.
Oh, I thought you said mean. Okay. C
What else
is
did I think?
now let's look at C. C says 75% above. If 75% is above, how much is below? The person who did the 2% answer before, you should know this. If 75% is above, how much is below?
25%.
That's right. And what is that called?
The lower quartile.
That's it. And we already found the standard score for that, right? In previous problem. How about if 10% is above? How much is below?
90.
That's right. That's the 90th percentile. So if 10% is above, that's the 90th percentile. And we also found out, I believe, well, actually we didn't, but if you open up the table, this one I don't think we've done before. The 90th percentile, we just have to scroll down here on the right, and it's right here, 0.90 is the 90th percentile. 1.28 is your standard score. Good, good. Now, here's a little bit of a challenge. Number 7. Number 7. A little bit of a challenge here. Let's see how good you are. Want to know what percentage of population is between two standard scores? Between -1 and 1. So let's look at the table. It's a little challenging, but it's not really that challenging if you think about it. Now, the standard score below -1, the standard score, the percentile for -1 is 16%. That means 16% is below. For +1, let's go down to where +1 is. It's 84% below. So -1 as a 16th percentile and +1 is an 84th percentile. What percentage is in between those two? See how good you are with that. Anybody want to try that? You have to sort of think about it mentally. or you can make a little drawing on a piece of paper with a bell-shaped curve, something like that.
Would it be 68?
68 is absolutely correct. Very good. How did you do it?
I subtracted 84 to 16.
Yeah, because the 84 percentile means 84% is below, which includes what's below the -1, right? It includes what's below the -1. So to find in between, you subtract what's below the -1, which is 16%. 84% minus 16% is 68%, right? Very good. How about between -1.28 and 1.75, using the same idea of subtraction? You're going to take your percentile, which is for 1.75, and subtract the percentile for -1.28. So let's look up 1.75 down here. Looks like it's 0.96. So 96% below 1.75. What's below -1.28? We have to go up a little bit, right? -1.28. 0.10. 10% is below it. What's the answer?
86.
86. Very good. Now this one's a little easier actually. Between 0 and 1. Now 0, a standard square of 0 is the median, is the mean. All right, the mean and the median are the same for a bell-shaped curve, and 0 represents the mean or median. All right, it's the middle. So a standard square of 1 is 84%. Can somebody tell me, without doing much math here, what would be the percentage in between? If you look at the standard square of 1, it says 84.
34?
34 is absolutely right, because you subtracted what? What did you subtract from 84%?
50?
50, because if 0 is in the middle, 50% is less than that. We know that 0 is the 50th percentile. You can see it down here anyway, but you should just know that. The 50%, that 0 is the 50th percentile. So you just take 84%, subtract 50%, you get 34%. Very good. And don't be surprised if you see a question like that on your next test. All right. And now that, again, this will be recorded, you'll be able to see this, and you'll be able to know how to do a problem like this, just using that table. All right. Now, we're not going to be doing very much more than this in the rest of the course. Somebody who's taking a regular stat course, the other course that I teach, will be doing quite a bit of this using their calculators, but not you guys. You just have to know a little bit how to figure these sort of things out. And this is probably the extent of using the normal curve that you'll be doing for the rest of the course, right? But it's helpful to know this so that you sort of know how a normal curve works, how we can find things with the normal curve. All right. Okay, and that's it for this chapter. All right, these are the types of things I wanted you to use, and actually I do have a couple more that I've circled. All right, yeah. Let me just show you one more here. Yeah, let me show you one more. 18. Look at number 18. One other type of problem that I might ask. Now, it says recall that for the standard Binet IQ scores, the mean is 100 and standard deviation is 15. All right. This is a bell-shaped curve for IQ scores. The mean is 100 for IQ, standard deviation 15, which is the average spread. Now, remember, the standard score, if I ask you if I give you a score, like 110 or 120, whatever, and you wanted to find its standard score, what you do is you subtract the mean, and then whatever difference you get there, you divide by the standard deviation. So for example, if the score is 115, You take 115, subtract 100, which is 15. You divide it by the standard deviation of 15, you get 1, positive 1. Okay. So what they're asking here, and this is using the empirical rule to specify the ranges in which 68%, 95%, and 99.7% of the scores fall. All right. Now, I will actually write this up for you and post it, this solution to this. But what you would do is you would need to know from the empirical rule in this chapter that you're looking for the percentage between -1 standard score and +1 standard score. That's the 68%. We found that before when we used the table, right? The empirical rule, which is talked about in the book, says that between -1 and +1 standard scores are 68%. We just showed that a minute ago. There's 95% between a standard score of -2 and +2, if you use the table. And between -3 and +3, 99.7%. Now, here is what they're really asking for here. They want to know, now that we know that, they want to know what actual IQ scores, in this case, would be the 68%, the 95%, or the 99.7%. So we would want to know what range of IQ scores would 68% of the IQ scores fall between. Now, how would you do that? Well, you would need to convert the standard score into the raw score, what we call the regular score, normal score, the score of the IQ score. And how would you do that? Well, you would use that same formula, which is the standard score is equal to the raw score minus the mean divided by the standard deviation. And you would just plug in to that formula the standard score on the left, and you will plug in the mean and standard deviation on the right of that equation, and then you would solve for the raw score. Now, I'm going to actually take this problem and post the solution to what I just said so you can see it, review it, and understand what I've just said. All right? Any questions about that? So don't worry about it. I will post this. And this is another type of possible calculation I can show you. All right? I'm not going to show you much more than what I'm talking about here. There's many more types of problems like this, but I think this is probably the best one out of those to show you this. All right. So I will post a solution to 18A. All right. They actually have the answers here, but I will show you the actual arithmetic behind it. All right. So that is for chapter 8. Let's actually now go to chapter 9, which has to do with some graphing. So let's go to the PowerPoint for chapter 9. All right. So let's actually look at some of the thought questions here. Suppose you have been keeping track of your living expenses and find that you spend 50% of your money on rent, 25% on food, 25% on expenses. You can draw either a pie chart or a bar graph to depict this information. All right. Now, if you tried this, which one would you prefer? Would you prefer a pie chart or a bar graph?
Pie chart.
Pie chart, yeah. Most people like the pie chart because you can see in the circle, each piece, there would be how many pieces of the pie? You have 3 pieces of the pie. 50% of the pie would be rent. 25% of the pie would be food, and 25% of the pie would be expenses. So typically you would have different colors maybe for the different pieces of the pie, and then there'd be a little key off to the side that would give the color, and then the name rent or food or other expenses, something like that. And most people prefer that over the bar chart. Now the bar chart would be, you would have a y-axis and an x-axis, and then along the x-axis you would have 3 rectangles, right? And the height of the rectangle would be these percentages, right? Now, the highest height of a rectangle will be 100%. So a quarter of that height would be food and expenses, and half of the height would be rent for each of those three rectangles. All right. Here's another plot. And what's the plot? It says over different time periods here would be some sort of production of what? Water between 1968 and 1992. And it says, give 2 reasons why this is not a good plot. Like, there's one good reason here this is not a good plot. Can somebody tell me?
It skips some years.
Yeah, you skip some years. That's right. You skip some years. However, it does seem there's some regularity in the years here. But yes, it's skipping some years, right? Like between there's 86, 87, and then there's something in between 90 and 91. Yeah. So there is some gaps in there. And how about the production? What's wrong with the production part of the graph? There's no numbers. There's nothing there. We don't even know what we're measuring here. It says water production, but in how is it being measured? There's nothing there. So this is a very misleading chart. We don't even know. You know, we see these line segments going up, going down. We don't even know how much they're going up or going down. They could be going. It looks like there's a big drop between 78 and 79 here, right? Around the 78, 79 period. We don't even know. This could be a tiny drop in production, but it looks big the way it's drawn. And we don't know without looking at the numbers. So very misleading chart. All right, anyway, suppose you had a set of data representing 2 measurement variables, namely height and weight for each of 100 people. How could you put that information into a plot, graph, or picture that illustrates the relationship between the 2 measurements for each person? So what would you do? So we have for each person, their height and their weight. How would you graph it?
Bar graph?
Remember, height and weight are numeric. Bar graphs are for categorical data, which is like what we just did.
Would you use a histogram?
Histogram, yes, that's a possible way of looking at it. However, we're comparing. So what we would have to have with a histogram, if we were going to do this, is we would have 2 pairs of rectangles, right? We would have to show both height and weight there. So it would be a little complicated with the histogram, but histogram is appropriate in the sense that it's for numeric data, which is what this says. Anybody else? There would be something even better than the histogram in this case here for comparing the height and weight. Maybe you haven't thought about it since high school. How about just the plain XY points?
Bar graph?
No, XY points.
Oh.
No, bar graph is for categorical data, not for this. This is numeric data, right? Height and weight is not categorical. They're going to be numbers, right? Measurements. No, the XY points, what we would call a scatter plot. It would be just a bunch of XY points that are plotted. And that's the type of thing we used to do when we did algebra, right? We would plot points and then draw a line through them. Remember that? That's what we're talking about here. That would be the best way of graphing. All right. Suppose you own a company that produces candy bars and you want to display 2 graphs. One graph is for customers and shows the price of a candy bar for each of the past 10 years. The other graph is for stockholders, that means people who own the company, and shows the amount the company was worth each of the past 10 years. You decide to adjust the dollar amounts in one graph for inflation, but to use the actual dollar amounts in the other graph. If you were trying to present the most favorable story in each case, which graph would you adjust for inflation? Now think about it. one of the graphs is for people who are going to buy the candy. Do you want you want the dollar amounts to be high or low for those people? People who are buying your product, do you want to show the numbers to be higher or lower? Think if you had your own company. Lower, of course, right? You don't want to show higher. So you would adjust it for inflation. What adjusting for inflation means is that you want to know how much the cost of the candy bars were based on dollars that were there that existed maybe 20 years ago, or excuse me, 10 years ago. Dollars that, because with inflation, prices go up, right? So, you know, hopefully you all know a little bit about inflation. It makes the dollar be worth less. So you want to adjust for inflation so that the price looks lower. Now, how about for your stockholders? You know, do you want to adjust for inflation with your stockholders? Remember, the stockholders are making money because they want to see low prices or high prices. Think if you own
Higher.
Higher prices.
Higher, of course. So you're not going to adjust for inflation for the graph for the stockholders. All right. Now, is that really? Aren't you sort of manipulating things when you do that? Yes, right. You're manipulating, and so you have to. The honest thing to do is to have a little statement explaining what you're looking at. You know, for the customers, you would have a little statement that says these numbers are adjusted for inflation. And for the stockholders, you would say these are numbers that have not been adjusted for inflation. Okay. So well-designed pictures or graphs. The data should stand out clearly from the background, clear labeling. You should have the title, purpose of the picture, what each axis, bar, pie segment stands for, the scale. Remember, we have to have a scale along each axis with starting points and numbers. You need to know where the data is coming from, and we don't want extraneous material, which means junk. You don't want stuff that's trying to distract people in the picture. We want as little of that as possible. All right. 3 types of pictures that are mentioned in this for categorical data. Categorical data, remember, is data that are labels, that are categories. Pie charts, bar graphs, pictograms. You need to know this because I typically ask questions on a test, multiple choice questions, where I will ask something like, which of these graphs are applicable for numeric data? Which of these graphs are applicable for categorical data? You should know the difference, all right? You should know the histograms, and you should know that scatter plots, dot plots, they're for numeric data. And you should know that pie charts, bar graphs, and pictograms are for categorical data, all right? You should just know that. And you should be able to remember that. Pie charts, again, categorical data. What are the categories? Hair colors. These are categories, right? If I say hair colors, here are 4 different types of hair colors. And they're asking what percentage of the whole fall into each of these categories, all right? So hair color has, in this case, brown, black, red, blonde, whatever. All right, so these are hair colors. They're categories. All right, hopefully that makes sense to you. All right, next one. Hold on a second. Bar graphs, same thing here. It says percentage in the labor force for years. Now you might say, well, wait a minute, years aren't categories. Well, they are in this case. We're not doing math with the years, are we? So they are sort of categories here. So this bar graph here is looking at the percentage or frequency of the whole falling into each category. So category in this case is a year. Percentage of men and women 16 and older and over in the labor force, all right? Percentage of men and women. Men are in the lighter bars, women are in the darker bars, all right? Notice how over time, we see that women have a bigger percentage in the labor force and men's percentage has gone down, right? The percentage of men in the labor force has gone down, percentage of women in the labor force has gone up over time. This is a bar graph, all right? We're not doing math. This is not a numeric. These years here are not numeric in the sense that we're not doing math with them. We're not measuring them. These are labels for different years. A pictogram uses pictures instead of rectangles. That's basically it. Now, here we're supposed to say percentage of PhDs earned by women. Now, take a look at these two graphs. Which of these two graphs is misleading? The one on the left or the one on the right? Which one is misleading? Which one is giving you a false impression?
The one on the left.
The one on the left. Now, the only thing that we're measuring here is the percentage for each of these categories. So it's the height of these scrolls. But notice what happens here. They make the scroll for psychology thicker than for biology, and the one for biology is thicker than math, making it look like it's a lot bigger of a difference than there is. And the one on the right is the actual difference in percentages. This one makes it look even more misleading because you're focusing on the size of the total area of these scrolls as opposed to just the height. So it's very important in pictograms and in bar graphs that you make the rectangles to be, or the objects, the pictures to be exactly the same width. Exactly the same width. And only the height we're paying attention to. Right? Now, the one on the right is not as appealing visually, but it's not misleading. Okay. Now, for measurement variables, when they say measurement variables, of course, they're talking about numeric or quantitative variables. Here are the ones that we use. Stem plots. We talked about stem plots. Histograms. Okay. Somebody had mentioned histograms earlier. Line graphs. All right. Scatter plots. Right. Here's a line graph which shows that the change of a numeric variable over time. Now you might say, well, wait a minute, I see years down here. Why isn't this categorical? Well, it's because what we're measuring is along the y-axis. You see that? This is different. So the measurement variable in this case is along the y-axis, and we're just seeing how it changes over time. This is a measurement variable that we're using the line graph for. This is the line graph of winning times for 500-meter speed skating in the Winter Olympics between these 2 years. Okay. Notice that the winning times have gone down over time. We know that, right? Any of you who've watched Olympics or any type of racing know that the winning times have gone down over time, right? We know that. People who run, the 100 meters or any other competitions, the winning times have gone down significantly over time. This is one of the graphs that shows that. Scatter plot shows a relationship between two measurement variables. Here's GPA and verbal SAT scores. Okay. You want to know whether the verbal SAT score, which is taken before you go to college, has any connection, association to your subsequent grade point average. It seems to show an upward trend here. It seems that the bigger the SAT score, the greater the GPA, but it doesn't seem like it's very strong. It's not a strong relationship. Picture drawing a straight line through this. It is upward sloping, but many of the points are far away from that line. But that's an appropriate line. appropriate plot the scatter plot so that we can compare two numeric variables. Now, what makes a disaster for these? Well, no labeling, one or more axes. We saw an example of that earlier. Not starting at 0, which could exaggerate the trends that we're looking at. Changes in the labeling on one or more axes, misleading units of measurement, poor information, all these things result in. Now let's take a look at. This was the one before that we looked at, the water production example, where there was no numeric values here. Right? Take a look at these two charts here, the same graph, right? The same graph here. And this one is shows between 0 and 40. And this one shows between 0 and 40. All right. Now, let's take a quick look at this here. They're telling two different stories. It looks like the same exact graph. Which one is it? We don't know unless it's labeled properly. That's the point. Notice for this graph on the right here, all the values are between 30 and 40, which means the changes aren't that much, right? There's not much of a change here. Here, the values run from 0 to 40. So it looks like the same exact picture. This one, these changes are much bigger, aren't they? Like this line going down goes from a little bit below 40 to almost 0. This one up here, when it goes down here, it goes from, looks like about 45 down to about 35. That's a much smaller change. So that's why you need to have labels. All right, you see the point? You see the point of doing this? We don't want to, you want to have these labels so we know what we're looking at. We don't know if this drop here is big or small. Up here, it's small. Here, it's big. Big change. And it's the same exact graph. Looks exactly the same. Not starting at 0. Not starting at 0. Okay. This is winning times for Olympic speed skating data with vertical axis starting at 0. Well, if you look at it this way, it doesn't seem like there's much of a change in Olympic speed skating times, right? Because it went down, you know, the times went from, what are these, in seconds, from about 43 down to about 37, maybe. So without starting at 0, you may think. Now let's go back. Let's go back actually to the slide that showed the speed skating time. Here's the original one. It looks like a dramatic drop, doesn't it? But that's because they didn't start at 0 along the y-axis, so it looks dramatic. But if you start at 0, which you should, that's what it looks like. Doesn't look so dramatic, does it? That's why starting at 0 needs to be there. Right? I think somebody had mentioned about gaps in graphs, right? Look what gaps do, right? A bar graph with a gap in the labeling, all right? So you go from February to 93, January 94, February 94, and there's a gap right in here, right? At first look, seems like the vertical axis starts at 0, but the bottom of the graph actually corresponds to 4%. So you got to be careful. The whole point of this, looking at all these things, you have to be careful when you look at graphs. It could be very, very misleading. Look at this thing here. All right. It says the distance between successive bars in the horizontal axis keeps changing. All right, the distance. Notice between 1939 and 1947 is 8 years. Between 47 and 51 is 4 years. 4 years, 8 years, 2 years. See, the differences between these years are changing, and yet the rectangles here make it look like that it's the same the same distance across each of the rectangles. It's not. Each of the rectangles are representing different number of years. So you could have labeling that's changing over time. Misleading units of measurement. It says in fine print, in $1971, the price of a 32-cent stamp in February 1995 would be 8.4 cents. So they put it down here in small print, and yet they show the true amount in 29 cents in 1991, making it look like, look how much postal rates have gone up. But in dollars or cents adjusted for inflation, it went from 8 cents up to 8.4 cents, which is a very small increase. So most of the increase is due to inflation. That's what this little thing's saying down here. But if you didn't read the little statement down here about adjusted for inflation, you would think there was a huge increase in postal rates. Again, misleading. All right. So there's more examples here, more examples. So look at the checklist here. It just mentions some of the things that we need to look for to make sure that we're looking at a graph that's honestly put together. Does the message stand out clearly? Is the purpose of title clear? Is the source of the data clear? Does it come from a reliable source? Is it clearly labeled with no chance of being ambiguous? The axis start at 0 or not? Do we have a constant scale along the x-axis? I mean, we've seen examples where the scale changes. Any breaks or gaps? The financial data, are the numbers adjusted for inflation? We noticed that it should be. Okay. Is there cluttering in the picture which makes it misleading, like that example with the scrolls? Right. All right, and this is another example, something that's misleading. We won't go into that, but you get the idea. So that is chapter 9. And what do you need to know from chapter 9? Basically, the types of graphs for categorical versus numeric, and then some of the things that could lead to misleading graphs. All right, just some of the features. It's possible there could be a multiple choice question that deals with that. All right, but so basically you have to know about the different types of graphs, and then a list of the things that you want to look for, like this checklist is here. Right. Can't really ask you too much more than that. All right, so that's chapter 9. See how we're doing with time. I think we could actually start going into chapter 10. I think that's a possibility. So let's stop for a minute, see if there's any questions about chapter 9. Any questions at the back here? I did not. So I think, let me just take a quick look at what I have here for chapter 9. No, see, I'm going to get rid of that also. This is from another textbook, so I apologize. I pulled up the wrong chapter 8 and chapter 9. It's from another course in another textbook. So it doesn't really apply to you guys. All right, so we've completed chapter 8 and chapter 9. So if you give me a second here, I'm going to pull up chapter 10. We'll get started with that. So let me just, as I'm doing that, let me just explain the quizzes. So there will be a quiz next, think about it. It would be next Tuesday that will cover chapters 7 and 8. And then next Thursday, 9 and 10. Okay, we'll have 2 quizzes next week. I will have chapter 10 completed by Tuesday. We'll get it started today. So I'll open it up that now. And I'll make sure the PowerPoints are also all right. Let's see if that chapter 10 open. Yep, there we go. All right, so let's go ahead and start chapter 10. Relationships between measurement variables. All right, now measurement variables again are quantitative variables. All right. Now, let's take a look at thought questions. We don't see the, actually, I'm going to, it's assuming that you have the book in front of you with the thought questions. So I'm going to actually go directly to the information for this chapter. And then we'll go, this is a chapter where we will have examples from the back of the book, because you do need to practice some of the arithmetic. I'm going to call it more arithmetic that you need to know for this course. Now, if we are comparing two quantitative variables, all right, we're going to create XY points for those quantitative variables, and we'll have a bunch of XY points showing on the graph, just like we did it in algebra in high school. We can measure the relationship between those two variables in what's called correlation. Correlation. Now here in the book, it says it measures the strength of a certain type of relationship between two measurement variables. I'm going to add something to this, and you should write this down, because it measures not only the strength, but the direction of this relationship. What do I mean by that? If we have a scatter plot and we draw a straight line through those dots, picture a straight line. When we learned about straight lines in high school, we know that we had lines that would be going up to the right, and we would call that positive slope. Remember that? Positive slope. It's like a stairwell going up. It would be sloping up towards the right. Then we would have lines that would be going down towards the right. All right. It's like we're going down a flight of steps. And that would be a negative slope. Correlation actually is like that. If we draw a line through our points, and the line is going up towards the right, and that is a positive slope, that means that the correlation would be positive. It'd be a positive correlation. That's called the direction. And then if the line that we draw through the points is sloping down, the correlation will be negative. And that would be called negative correlation. That would be the direction. That's what we mean by direction, positive or negative. Strength. Now, we'll talk about the strength in a minute. But the whole idea of strength is how, when we draw a line through some points, how close are those points to the line? The closer the points are to the line, the stronger is the correlation. And the further apart the points are from the line, the weaker the correlation. And that's what we mean by strength. So correlation measures the strength and direction. That's what I'm saying. You might want to write that down, of a certain type of relationship between two measurement variables. What type of relationship? Linear. Linear. L-I-N-E-A-R. Linear. Linear means line. All right, linear. Doesn't measure a nonlinear relationship. Doesn't measure a curved relationship. It measures a linear relationship. Now, regression is a numerical procedure or method where you try to predict one measurement variable from another. And how do you do regression? Well, there's a mathematical procedure which you don't need to know. It's from calculus. You don't need to know calculus. And what calculus allows you to do is find the line that best fits those dots, those XY points that you plot, okay? It finds a line that best fits them. And that line will have a slope and will have a y-intercept. If you remember, y is equal to mx plus b, when you learned lines in algebra, we're going to be using the same type of line. It's the same thing, same equation, and that is called the regression line. Once we know the regression line, we can, if we're given an x value, we can plug it, we can replace the x in the equation with that number, and then multiply that by the slope and add the y-intercept like we did in high school, and we would get our y. That would be the prediction that we would get. All right, and then again, I will show you examples. It's very easy to do because I'm going to give you enough information that you can do it very easily. All right, now, one of the things, this is very important, one of the things that I would like for you to do, I hope all of you have Microsoft Excel on your computer. And if you don't, then I probably will have an alternative for you, but hopefully you all have Microsoft Excel. I don't know if you've ever used Excel, but I will show you how to find things using Microsoft Excel. It's very easy to use for what I'll be showing you. You don't have to be, an expert user. If you've never used it before, again, I will, when I show you the examples, I'll show you on Microsoft Excel. You will be able to use Microsoft Excel for your tests, all right? So it's open book and also open software where you can use Microsoft Excel. And then you'll see how easy it is to find things like correlation, because there are in Microsoft Excel functions that you can use, very easy to use, and you can easily find the correlation between two variables using it. And you can also find the slope and y-intercept of your regression line. Microsoft Excel is able to do that. And actually, people who've taken statistics in high school, this is how it's taught. It's taught with Microsoft Excel. All right, so I will show you that next time, those examples. So here's another important thing. One of the things that we're going to be looking at in this course is the difference between a statistical relationship versus a deterministic relationship. Now, and I'll give you a simple example. When you were in high school and plotting a straight line, you would have dots, XY points that would fall exactly on that line, right? That's how you came up with the line. But not so in statistics, because data is not like that. Data is variable. It changes. So even though we can see the XY points look like they are upward sloping or downward sloping, it's not going to, the points aren't going to all fall on that line that we draw. There's going to be some points, many points actually, that will not fall on that line. So that's called a statistical relationship because of the variability in our measurements. And so it's more real life than what we learned in high school. High school was more hypothetical. Here we're learning real data, real life, and we're drawing a straight line that approximates that relationship as opposed to a straight line that is absolutely determined, okay? So that is the difference. And also there's another idea of strength versus statistical significance, right? Now, what does statistically significant mean in the language of statistics? It says here, if we look at a sample and we discover a relationship between maybe two variables, it says here the chances of observing the relationship in the sample when actually nothing is going on in the population is less than 5%. What does that mean? That means that if we're looking at a relationship and we think that the probability that this is just normal variable, just normal chance, there's no real relationship at all, but what we're looking at is just something, a fluke. We're looking at something that's a fluke. Well, if the chance of that fluke is less than 5%, then we will conclude that this relationship is actually significant. It's not just it's probably not a fluke. There's a 95% chance it's not a fluke, all right? We'll show examples of that later. Now, you might say, all right, fine. Whatever we're using in statistics will tell us whether something's a fluke or not a fluke. how about the actual strength of that relationship? Does the statistics show that? Well, you will see the strength, but if something is significant, statistically significant, it does not mean there is a strong relationship between the two variables, all right? It doesn't mean that. It just means there is a statistically strong relationship. And again, you may think, well, what's the difference? I will show you that a little bit later in the course, all right? But that's what they mean here. And actually, they're going into it a little bit more here. They say even a minor relationship will achieve statistical significance if the sample is very large. So if you have a very large sample, it's very easy to find a relationship between two variables. This is the point. Even if the actual relationship is minor. On the other hand, you can have a very strong relationship between two variables, but if the sample size is too small, we won't be able to determine a statistical significance. Now again, we'll put this off till a little bit later. I'll show you examples of what I mean by this a little bit later in the course. It may not be clear to you what I mean by that. All right. And again, they're actually giving you an example of this here. So actually, let's look at the example. I think so. Look at it. It says working nights may increase breast cancer risk. So the researchers wrote this up and said the numbers in our study are small, but are statistically significant. In other words, they're not seeing much of a relationship between working nights and breast cancer risk. They don't see, it's a minor relationship, but because they had a large number of people in the study, in this case, nurses, 78,000 is a very large study, all right? It found that nurses who work night shifts at least 3 times a month for 1 to 29 years were 8% more likely to develop breast cancer than those who didn't, all right? So the point of the matter is, if you have a very large number of people in the study, you will find statistically significant relationships when they are really, in real life, very significant. All right, so that's the point of that study there. Okay, now let's move beyond that. Let's talk now about correlation. Correlation is sometimes represented by the small letter R, sample correlation. What does it measure in general? Because it is a numeric value that you will get. It measures how closely the values fall to a straight line. In other words, the stronger the relationship is, the closer the values are to a straight line. But it measures only linear relationships and not nonlinear relationships like curves. Now, here's something that's very important that you should know. Correlation, when it's a number, and it goes from -1 to +1. That's the range of values between -1 and +1. What's -1 mean? Perfect negative linear relationship. It's a perfect negative linear relationship. In other words, you draw a line that's sloping downward, and every point in the data set falls on that line. Now, are you ever going to see anything like that in real life? No. But that's the type of line we used to see in high school, right? Downward sloping line, all the dots were on the line. +1 correlation means perfect positive linear relationship. That means we have an upward sloping line and all the dots fall on that line too. Never see it. We'll never see that. Okay. So in real life, you're going to see numbers between -1 and +1. In other words, decimals. Now, correlation of 0 indicates no linear relationship between two variables. And what's the best line that you can draw through no linear relationship? A horizontal line. I don't know if you remember this, but when you draw a horizontal line, it has a 0 slope. zero slope. So correlation of 0 corresponds to a horizontal line, which has a slope of 0. It indicates no linear relationship between the two variables.
So the correlation of 0 we'll be dealing with mostly where it's horizontal, because you said it was in between +1 and -1.
We would see that in data sets where there's no linear relationship between two variables. We'll see correlations close to 0. Very rarely will we see 0. We'll see numbers close to 0. So any numbers that are negative close to 0 or positive close to 0, like I'll give you an example, -0.05, that's close to 0. Positive 0.08, close to 0. Those you can pretty much say have a no linear relationship because it's very close to 0. All right, does that make sense? And I think, let me just take a quick look here. Let me show you some examples here. Well, this one here is that GPA, looking at the relationship between GPA and verbal SAT scores. And notice that the relationship is upward sloping. If you could see it, right? Upward sloping towards the right. But if we drew a straight line through these points, many of these points would not be near the line, right? It would be scattered away from the line. Notice the correlation is 0.485. All right, that's a moderate positive relationship. You could see it's going up towards the right, right? As the verbal SAT scores increase, it seems like the GPAs are going up, but it's not really strong. It's moderate. 0.485 is almost halfway between 0 and +1. So there is a relationship, but it's not exact. It's nowhere even close to being strong. All right. Oops. Sorry about that. Let's do the next one. Look at this one here. All right. Age of wife, age of husband. Would you agree that this is a not only positive relationship, but it's very strong? You picture a line going through this, and most of the dots are very close, would be close to that line, wouldn't it? Notice it's not as scattered as the previous example. Look at the previous one. More scattered, right? Seems to be going up towards the right, but it's more scattered. Notice this one. Most of these points are going to be very close to the line. Look at the correlation, 0.94, very close to +1. That is a strong positive linear relationship between age of wife and age of husband. And it sort of makes sense, right? Their ages should be close. But look at this one here. This is the same husbands and wives, but now we're looking at their heights. Not as strong, right? Notice they're a little more scattered, but it does seem to be going up towards the right. Notice the correlation is positive 0.36, moderate, close to weak, but I would say moderate, positive linear relationship. Not as strong, moderate, or even weak if you want to say weak. And you could tell if I drew a line through these points, that many more of those points would be further away from the line. You can see the difference between these two. This is strong, this is not so strong. Both positive, however. Look at this one. Relationship between some sort of prestige rating. I don't know what that is. Prestige, oh, for occupation. How prestigious the occupation is of the person that you're looking at, and then suicide rate. Notice that it doesn't seem like there's hardly any positive or negative relationship. Hardly anything here. And to be honest with you, see this point up here? If we remove that point, it looks like it's actually sloping slightly down, doesn't it? That point is actually making it go up a little bit, correlation. Correlation is positive 0.109. That is no, I would say that would be very weak positive correlation. And notice it says here, if you remove this point, correlation drops to 0.018, which is practically zero. Practically zero. So in this case, we would say no linear, very little, very weak linear relationship, if any at all. We would say probably no linear relationship. Right? All right. So anyway, we're going to stop right here. We still have a few slides left. We're going to continue with this and we'll go to chapter 11. So we're going to finish 10 and 11 on Tuesday and have the first quiz, which will cover chapters 7 and 8. And then we're going to do chapter 12 on next Thursday. And we'll have our second quiz, which will cover chapters 9 and 10. If that's the way we're doing it. All right. And then we'll have obviously a quiz the following week. But once we finish chapter 12, we will have completed all the things that we need for test number 2. So the week after, we're going to have a review and also a test for number 2. And we'll have another quiz too, which will cover chapters 11 and 12. All right. So that's the plan. So fortunately today we got into chapter 10, and I think we should be able to make up our lost ground very easily next week. And again, we'll have 2 quizzes next week, and we'll complete number 10, 11, and 12 next week. And then in the following week, we'll have a review and our test number 2. And we'll have, I think, a third quiz also. Another quiz that week also. All right. Any questions about anything? So we stopped at number 17 here. I'll make a note of that, and we'll finish this next time. No questions? Okay, so I'll stop the recording, and I will see you guys next Tuesday. All right, take care.